Open your mind. Let the conversation begin.
Imagine it is maybe 3 in the morning.
Very late, yeah.
Right. And you are an astronomer sitting in a very cold, very quiet observatory. Or, well, actually more likely these days, you are in a server room somewhere, far from the actual telescope.
Yeah, just staring at screens.
Exactly. You are staring at a high-resolution monitor. You are running these comparison images of the night sky, taken just days apart. And, the stars are fixed, right? They do not move relative to each other over a Tuesday and a Thursday.
No, they do not.
But then you see a pixel.
Just a tiny speck.
A tiny, faint, almost insignificant gray smudge. And it is in one position on the first image and then slightly shifted on the second. So you track this anomaly.
As you should.
You plug the astrometry into your software, you calculate the orbital arc, and suddenly the computer spits out an intersection point. Earth's orbit and this rock's orbit occupying the exact same physical space on a very specific date in the future.
That is the nightmare.
It really is. You are sitting there, basically the only person on the planet holding a cup of cold coffee, realizing you have just calculated a mathematical timeline to the end of the world. Welcome to the Mind Lounge.
It is the ultimate nightmare scenario for the astronomical community.
Oh, without a doubt.
And while that cinematic vision, a rock hurtling toward Earth feels like pure science fiction, the mechanics behind it are incredibly real. How we discover these objects, how society would react, our massive observational blind spots, and, well, the physics of kinetic deflection, it is all deeply rooted in modern science.
Right. And that is exactly our mission for this deep dive today. We are taking you on a journey into planetary defense. We are going to look at the hard data we have on near-Earth objects, especially the asteroid Apophis.
A fascinating case study.
Absolutely. We're going to dig into the physics of our solar system and how the threat of an impact forces us to confront some very uncomfortable truths about our civilization.
It forces a mirror on us, for sure.
So we're going to use that 3 a.m. discovery as our baseline, just a thought experiment to help us understand the stakes, before we pull back the curtain on the actual science happening right now to prevent it. Because the line between a thought experiment and historical reality is, well, it is much thinner than you might think.
Very thin.
So let's stay in that observatory for a minute. You have this data, you have a timeline, but a short observational arc, like just a few days of tracking a pixel, that must have massive margins of error, right?
Oh, massive, huge margins of error.
So how do you even begin to confirm something like this without causing absolute pandemonium? Who do you tell first?
You hit the nail on the head regarding the error margins. When an object is first discovered, we really only have a tiny fraction of its total orbit recorded. Think of it like watching a car drive on a massive circular racetrack.
Okay, I am picturing it.
But you only get to see the car move for 2 inches.
Oh, wow. Just a tiny sliver.
Exactly. And from those 2 inches, you have to mathematically project exactly where it will be 3 hours from now. Small errors in your initial measurement, they compound over distance and time.
Right, because the tiny angle shift at the start means you are miles off by the end.
Precisely. So the astronomer at 3 a.m. doesn't just call the press. They do not tweet it out.
Hopefully not.
Right. They submit the coordinates to the Minor Planet Center.
The Minor Planet Center, what is that?
It is the official worldwide node for observational data on minor planets and asteroids. It is basically a global clearinghouse.
So it just goes into a database. But who is checking the math? Like, who verifies it?
An entire global network. Once the initial coordinates are logged, automated systems and other astronomers around the world, they point their telescopes at that exact patch of sky to get follow-up observations.
To see if they can spot the same pixel.
Exactly. We call this extending the observational arc. Every new data point tightens the math. It shrinks what we call the error ellipse.
The error ellipse. Okay, define that for us.
The error ellipse is simply the region of space where the asteroid could potentially be on a given date, based on the math. But here's where the geopolitics and the psychology really kick in.
Right, the human element.
Yeah. As that error ellipse shrinks with more data, if the Earth remains dead center inside of it, the probability of impact spikes. It moves up the Torino scale.
The Torino scale.
Yep.
That is the metric astronomers use to categorize the impact hazard of these near-Earth objects, right?
That is right. It goes from 0 to 10. 0 is no hazard. 10 is certain collision causing global catastrophe.
Okay, I want to pause on the psychology of that, because there is a very fragile threshold between quiet scientific verification and a global security crisis.
Extremely fragile.
Right. Let's assume the math holds up in our thought experiment.
Error.
Errorless shrinks, and Earth is an absolute bullseye. How does that information actually get out? I mean, if I am a government, my first instinct is probably to classify everything.
Naturally.
Just to prevent mass panic while we figure out a solution behind closed doors.
Governments would certainly try to do that. But classifying the sky is fundamentally impossible.
Because anyone can look up.
Exactly. The astronomical community is deeply international and surprisingly decentralized. You have amateur astronomers with incredibly sophisticated backyard rigs.
Like people just in their driveways.
Yeah. And they track the exact same data the Minor Planet Center does. If a massive object is suddenly the focus of intense follow-up observations from major observatories globally, people notice.
Right. The amateurs would see all the big telescopes pointing at one spot.
Precisely. If a government tries to suppress a verified Torino-scale 10 event, it would inevitably leak. And honestly, a leaked apocalypse scenario is far more dangerous than a managed disclosure.
Why is that? Because of the breach of trust.
Exactly. It instantly destroys institutional trust. If the public finds out the government hid the end of the world, civil order evaporates immediately.
You just lose all authority instantly.
Instantly.
Which means disclosure would have to be coordinated, fast, and transparent. But even if it is managed perfectly, the moment the news breaks, we hit a wall. In our thought experiment, let's say the countdown clock is 10 years.
A decade. Okay.
The sources for our deep dive today discuss the narrative of societal collapse. And the most striking takeaway for me is that the collapse does not begin when the rock enters the atmosphere. It begins the very second the news is confirmed.
Absolutely. The anticipation of the event is almost as destructive as the kinetic impact itself. It is just on a different timeline.
Right.
Think about our modern world. Everything from global supply chains to the stock market to the value of fiat currency, it is all built on one massive invisible assumption.
That tomorrow will happen.
Yes,
Yeah.
that there is a stable future to invest in.
Wow. Yeah, if you know a city killer asteroid, which is a term straight out of our research,
Yeah.
is going to impact Earth in 10 years, why would you go to work?
It wouldn't.
Why would a farmer harvest crops? I mean, money only has value if there's a future where you can exchange it for goods.
Exactly. If the future is effectively canceled or at least severely compromised, the entire psychological foundation of the economy just vanishes overnight.
So what happens the next day?
You would see an immediate, unprecedented freezing of global logistics. We operate on just-in-time supply chains, right?
Right. Warehouses don't hold months of inventory anymore.
No. Grocery stores only have about 3 days of food on the shelves at any given time. If truck drivers decide to stay home with their families because, well, the financial system has crashed and the money they are paid is suddenly worthless,
Then the trucks don't move.
the trucks don't move. Major urban centers become starvation zones within a week.
That is terrifying.
It is. The social contract relies on the promise of mutual, ongoing benefit. When a definitive endpoint is established, that contract shatters long before the asteroid even crosses the orbit of the moon.
Okay, let's fast forward through that societal breakdown. It is bleak, but let's say we reach 0 hour. The rock is here. I think people have a very skewed perception of what an asteroid impact actually is.
Mostly because of Hollywood, yeah.
Exactly. We picture a giant fireball, like a massive bomb going off. But it is not a bomb. It is not an explosive device with a fuse. It is just a rock.
Just a rock.
So where does all the destruction actually come from?
The destruction comes entirely from kinetic energy. We have to look at the physics equation for kinetic energy, which is mass times velocity squared divided by 2.
Okay, math time.
Don't worry, I will keep it simple. These objects are traveling at cosmic velocities. We are talking upwards of 40 to 50,000 miles per hour relative to Earth.
50,000 miles per hour. That is hard to even conceptualize.
At those speeds, the atmosphere acts less like a cushion and more like a brick wall. When a massive asteroid hits the atmosphere, the air in front of it cannot get out of the way fast enough.
So it just piles up.
It compresses instantaneously.
And compressing a gas rapidly heats it up, right? Like putting your thumb over a bicycle pump, but on a planetary scale.
Precisely. The air superheats to temperatures hotter than the surface of the sun. The asteroid itself begins to vaporize. Now, depending on the angle, the speed, and the composition of the rock, It might not even make it to the ground.
Wait, really? It could just blow up in the sky?
Yes. If it is a loose rubble pile of silicate, for instance, it might experience an airburst. This is when the pressure differential between the front and the back of the asteroid causes it to violently pancake and disintegrate in the mid-atmosphere.
Wow.
All of that kinetic energy is released in a fraction of a second. It creates a massive shock wave, an overpressure wave, that propagates downward.
So it flattens everything below it.
Yes, flattening cities like a massive thermonuclear detonation, but, without the ionizing radiation.
If it is solid, if it is like iron and it does hit the ground.
If it is an iron nickel chunk large enough to survive entry and strike the crust, the energy release is just incomprehensible. It instantaneously vaporizes the rock, the ground, and everything in a massive radius.
Just gone.
Gone. It punches a crater into the Earth, sending a shockwave right through the tectonic plates. But worse, it throws millions of tons of pulverized, superheated rock, which we call ejecta, up into the stratosphere.
And that has to come back down.
It does. It falls back down globally, heating up upon re-entry and potentially igniting global firestorms.
Which brings us to the most terrifying part of this entire sequence, the aftermath, the result. In our scenario, the initial blast is over. The survivors are, crawling out of the rubble.
Right.
And the assumption is usually, okay, the worst is over, we survived the hit. But the sources for this deep dive suggest the hit is really just the opening act. And here's where I really need to push back, or at least ask for some heavy clarification.
Sure, go ahead.
The research states that we aren't just guessing about this aftermath. The text claims there is evidence of a massive cosmic impact that actually happened 12,800 years ago.
The Younger Dryas impact hypothesis, yeah.
Wait, 12,800 years ago, humans were around that.
Absolutely.
We had complex hunter-gatherer societies. If an impact of this magnitude happened while humanity was walking the Earth, where is the giant, undeniable crater? Why isn't this the first page of every history book?
That is exactly the right question to ask, and it is why this hypothesis has been a subject of such intense scientific debate.
So where's the hole in the ground?
Well, the answer is that we might not be looking for a single massive crater on land. The Earth is 70% water. An ocean impact would leave a vastly different geological footprint.
Oh, so it could be underwater.
Right. Potentially buried under miles of sediment or deep oceanic trenches today. Alternatively, it could have been a massive airburst, like we just talked about, or a fragmented comet hitting the massive Laurentide ice sheet that covered North America at the time.
Oh, I see. Hitting ice instead of rock.
Exactly. 2 miles of ice would absorb the physical cratering, but it would still release the catastrophic energy.
So if there isn't a textbook crater, what is the actual hard evidence? Because I have to admit, maybe it hit the ice sounds a bit convenient.
It does sound convenient, which is why scientists rely on proxies. Geological and chemical markers left behind. Across 4 continents, researchers have found a very specific, distinct boundary layer in the soil dating back exactly 12,800 years.
4 continents, that is a global footprint.
Yes. It is often referred to as the black mat. Below this mat, you find the remains of megafauna, mammoths, saber-toothed cats.
Right, the Ice Age animals.
And you find evidence of early human cultures, like the Clovis people in North America. But above that layer, the megafauna are completely gone, and the human population density drastically drops.
Wow. So something happened right at that black mat layer.
Something huge. And more importantly, inside that incredibly thin boundary layer, scientists find millions of nanodiamonds.
Nanodiamonds.
Yes, tiny microscopic diamonds, which are only formed under extreme shock and pressure. They also find melt glass.
Like from heat.
Extreme heat, similar to what was found at the Trinity nuclear test site. And they find elevated levels of platinum and iridium.
And those aren't common on Earth, right?
Exactly. Elements that are rare in Earth's crust, but abundant in asteroids and comets.
Okay, so the chemical signature of a massive cosmic event is literally buried in the dirt. But if it hit an ice sheet or exploded in the air, how did that cause a mass extinction? How does that wipe out the mammoths and essentially reset early human civilization?
Because of the rapid climate shift. The true danger of a massive impact isn't the explosion itself, it is the environmental collapse that follows.
The aftermath.
Right. When an object hits with that much energy, especially if it strikes an ice sheet, it instantly vaporizes massive amounts of water. It throws enormous quantities of dust, ash, and water vapor into the upper atmosphere.
So it basically creates a shield around the Earth.
A blanket of ejecta that blocks out the sun's visible light.
So we are talking about an impact winter.
Exactly, an impact winter. The explosion is a localized tragedy, but the climate shift is a global extinction filter. If you block the sun, global temperatures plummet within weeks.
Weeks, not years.
Weeks. In the case of the younger Dryas period, ice core samples from Greenland show that global temperatures crashed incredibly fast, plunging the planet back into near-glacial conditions for over 1,000 years.
It's 1,000 years of winter.
And furthermore, if the impact melted a massive portion of the North American ice sheet, it would have dumped millions of cubic miles of fresh water into the Atlantic Ocean.
Which would mess with the ocean current.
It disrupts the ocean's thermohaline circulation. The currents that distribute heat around the globe just shut down.
So the food chain just completely collapses. Photosynthesis stops, the plants die, the herbivores starve, the predators starve.
The whole system breaks.
And the human survivors of the initial blast, they are suddenly thrust into this freezing, dark, and starving world. It is literally a complete reset of accumulated societal progress.
Yes. It forces humanity back to the absolute basics of raw survival. Infrastructure, accumulated knowledge, tribal networks, they are all dissolved by the sheer necessity of surviving the next winter.
And that historical precedent is, frankly, the perfect, terrifying mirror for our modern thought experiment.
It really is. It shows what is actually at stake.
Okay. That is incredibly heavy. Just the realization that our entire modern world sits on a geological layer that contains the pulverized remains of a cosmic reset. It is a lot to take in.
It is a sobering thought.
But let's pull ourselves out of the past and out of the hypothetical. Let's look at the reality of our solar system today. Let's talk about Apophis.
Ah, Apophis, the rock that got everyone's attention.
Yes. Our sources give us very specific data on this rock. It was discovered in 2004, and when astronomers first calculated its orbit, they got a date, April 13th, 2029. And it caused a massive panic, didn't it?
It absolutely did. When Apophis was first discovered, its initial observational arc placed Earth squarely inside its error ellipse for that 2029 date.
So we were in the crosshairs.
We were. It was given a Torino scale rating of 4, the highest rating any object had ever received at the time.
A 4 out of 10. That doesn't sound too bad on paper.
Well, a rating of 4 means a close encounter, meriting attention by astronomers, with a 1% or greater chance of collision capable of regional devastation.
Oh. A 1% chance of regional devastation is actually terrifying.
For a brief period, the math suggested a very real possibility that a rock, roughly 1,100 feet across, was going to strike the Earth.
1,100 feet.
Yeah.
That is like the Eiffel Tower, but made of solid rock, moving at cosmic speed.
Exactly.
But the math got better. The panic subsided. Our sources confirm that NASA has definitively ruled out a 2029 impact. They tracked it longer, the error ellipse shrank, and Earth was no longer in the center.
We can all breathe.
Yes, the 2029 impact is off the table.
But here is where the data gets unsettling again. It is going to miss us, but it is going to pass within 19,000 miles of Earth.
A very, very close shave.
Now, to ground that number for you listening, 19,000 miles is inside the orbit of our geosynchronous satellites. The satellites that provide our television signals, our weather data.
They sit at about 22,000 miles up. Apophis is literally going to thread the needle between those satellites and our atmosphere. It is an astronomical near miss.
It is. It is a phenomenal opportunity for observation, but it also introduces a massive variable into our long-term safety.
What do you mean?
Well, this is where the physics of the solar system get incredibly complex. The sources highlight that the real danger of a 19,000-mile pass isn't the flyby itself. It is how Earth's gravitational influence will alter Apophis's path for the future.
Right, because gravity isn't just, things falling straight down. It warps trajectories. If I understand this correctly, it is like a gravitational slingshot, right?
Yes, exactly.
Like when we send a probe to Jupiter, we fly it close to Venus to steal a little momentum and change its direction. The Earth is about to do that to Apophis.
That is an excellent analogy. We're dealing with an n-body problem, specifically the interaction between the immense mass of the Earth and the much smaller mass of the asteroid. As Apophis dives into Earth's gravity well at 19,000 miles, its trajectory will be bent significantly. It will come in at one angle and leave at a completely different one.
That makes sense.
And the crux of the issue is calculating exactly what that new angle will be. Astronomers are looking for what are known as gravitational keyholes.
Gravitational keyholes. Okay, you have to explain exactly what those are because that sounds like a sci-fi concept, but I know it is hard math.
It is very hard math. A gravitational keyhole is a tiny, incredibly specific region of space near a planet. We are talking about an area that might only be a few hundred meters across.
Just a few hundred meters.
Yeah.
Out in space.
Yes. If an asteroid's trajectory passes through the exact center of one of these keyholes during a flyby, the planet's gravity will bend the asteroid's path so perfectly that it guarantees a direct impact on a future orbit.
Whoa. So it is literally threading a cosmic needle.
Exactly.
If Apophis passes through a random point at 19,000 miles, it gets bent into a harmless orbit. But if it happens to pass through a 500-meter wide keyhole during that flyby, the Earth's gravity acts like a sniper.
Adjusting its aim.
Right, adjusting the asteroid's aim so that when it comes back around in, say, 2036 or 2068, it hits us dead on.
Exactly. A near miss is a profound physical interaction, and making those calculations is agonizingly difficult because of something called the Yarkovsky effect.
The Yarkovsky effect. Okay, what is that?
So asteroids are rotating bodies. As an asteroid gets closer to the sun, the side facing the sun heats up.
Like pavement on a hot day.
Right. Now, as the asteroid rotates, that hot side turns toward the cold vacuum of space, and it radiates that heat away as thermal photons.
Okay, I am with you.
That tiny emission of thermal radiation actually acts like a microscopic thruster. It gently pushes the asteroid over time.
Wait, just the heat radiating off the rock acts as a thruster.
Yes. It is an incredibly small force, but over decades, it can alter an asteroid's orbit by hundreds of miles.
That is mind-blowing.
So, to know if Apophis will hit a keyhole in 2029, we don't just have to map its current trajectory. We have to calculate exactly how much heat it is absorbing and radiating over the next several years.
We are trying to calculate the thermal radiation of a rock millions of miles away, just to see if our own planet's gravity will accidentally slingshot it back into our ices decades from now.
That is the reality of planetary defense.
Wow. But at least with Apophis, we're doing the math. We know it is there. We can track the Yarkovsky effect. We can look for the keyholes.
We have eyes on it.
But as our sources pivot, they introduce a threat that is, honestly, infinitely more terrifying. Because Apophis is visible, the real danger lies in the objects we cannot see, the blind spots.
This is the most glaring vulnerability in our entire planetary defense framework.
How so?
Humanity's ability to observe the universe is almost entirely dependent on catching photons, catching light. For near-Earth objects, we rely on sunlight reflecting off the surface of the asteroid against the black canvas of deep space.
Right. We are looking for lit-up rocks in the dark.
Yeah, exactly. But the geometry of our solar system dictates that we can only effectively look outward, away from the sun, toward the asteroid belt, Jupiter, and beyond.
Because if you look inward, you are staring directly into the sun's glare.
You are blinded.
The sources explicitly state that city-killer asteroids can remain completely hidden in this glare. I think of it like driving west on the highway exactly at sunset.
That is a great comparison.
Right. The sun is blazing right in your eyes. You drop the visor, you put on sunglasses, you squint, but you are effectively blind. There could be an 18-wheeler stalled in the middle of your lane, and you would not see it until your bumper hit it.
That is essentially what we are dealing with on a planetary scale. Yes.
Seriously.
Seriously. Optical telescopes, the massive instruments we use to scan the skies, they have incredibly sensitive digital sensors. If you point them anywhere near the sun, the sheer volume of solar radiation would instantly fry the instruments.
So they just don't look there.
They cannot look there. So we have a massive, unobservable cone of space pointing inward toward the center of the solar system. Asteroids, whose orbits keep them primarily interior to Earth's orbit, meaning they orbit closer to the sun than we do, they can approach us from the day side of our planet.
From the daytime sky.
Yes. We would have zero warning.
Zero warning. No 2004 discovery for a 2029 flyby. No 10-year countdown like in our thought experiment.
None. In fact, this isn't even theoretical.
Oh, great.
In 2013, a relatively small asteroid about 20 meters across entered the atmosphere over Chelyabinsk, Russia.
I remember the videos of that, the dash cam footage.
Exactly. It came from the direction of the sun. No observatory on Earth saw it coming. It detonated in an airburst with the energy of roughly 30 Hiroshima bombs.
And we didn't see it until it exploded.
Right. It blew out windows across the city and injured over 1,000 people. And that was just a 20-meter rock.
20 meters.
Yeah.
That is nothing compared to Apophis.
The sources note that objects large enough to be classified as city killers, objects hundreds of meters across, can and do lurk in that same solar blind spot.
That is deeply unsettling. We have supercomputers, we have the James Webb Space Telescope looking at the literal edge of the universe. But a mountain of rock could be sneaking up on us right now just because it is hiding behind the sun's glare.
It highlights the immense fragility of our observation systems.
It really does.
Sure.
But the sources don't leave us completely defenseless here. They introduce a massive paradigm shift in how we handle this. Let's talk about lighting up the dark. Let's talk about NASA's NEO Surveyor.
Yes. The NEO Surveyor is the answer to the sun glare problem.
How does it work?
Well, for decades, our approach to planetary defense has been largely passive and ground-based. We wait for nightfall, we open the observatory domes, and we scan the dark patches of sky. Then NEO Surveyor is a space-based telescope.
Which immediately removes the distortion of Earth's atmosphere.
Yes, but more importantly, it does not rely on visible light. It operates in the infrared spectrum.
Okay, break that down for us. Why does infrared bypass the sun's glare? If the sun is emitting visible light, isn't it also emitting massive amounts of infrared heat?
It is, but the mechanics of detection change entirely. Asteroids are generally very dark objects. They do not reflect much visible light, making them hard to spot even in deep space. However, as they absorb solar radiation, they heat up.
Just like the Yarkovsky effect you mentioned earlier.
Exactly. Even if they are incredibly cold by our terrestrial standards, they are much warmer than the near absolute zero of the vacuum of space around them.
Ah, contrast.
Yes. The NEO Surveyor is designed to look for that specific heat signature.
So instead of looking for a dark rock reflecting a tiny glint of sunlight, you are looking for a glowing ember against a freezing background.
Precisely. And by placing the telescope in a specific orbit, likely the Earth-Sun L1 Lagrange point, which allows it to maintain a stable position between the Earth and the Sun.
It just sits there watching.
Right. It can continuously scan the space near Earth's orbit. It picks up the thermal emissions of these objects, even if they are in regions where the visible glare of the sun would normally blind our optical sensors.
That is brilliant.
Yeah.
It is a dedicated sentinel.
It shifts our posture from passive stargazing to active, aggressive planetary defense.
I love the idea of taking the blindfold off. We are finally mapping the potholes on the highway before we hit them.
Exactly.
But observation is really only the first step, right? Finding a city killer coming out of the sun's glare, or calculating that Apophis is going to thread a gravitational keyhole, that doesn't actually save us.
It just gives us the timeline.
Right. Knowing the exact date and time the world ends just means you know exactly when to panic unless you can actually do something about it. And that brings us to the most incredible part of this entire deep dive, NASA's DART mission. We aren't just watching anymore. We learned how to punch back.
The DART mission, the Double Asteroid Redirection Test, it is arguably one of the most consequential engineering achievements in human history.
The text refers to it as a kinetic impactor. But let me push back here, because Hollywood has trained us all to think very differently about this.
I know exactly where you're going with this.
Right. If an asteroid is coming, the movie logic is that we send a team of drillers with nuclear warheads to blow it into a million pieces. Why are we using a kinetic impactor instead of just nuking the thing? Wouldn't blowing it up solve the problem instantly?
Blowing it up is perhaps the worst possible strategy you could employ.
Really? Why?
If you detonate a nuclear device inside an asteroid, you have not eliminated the mass, you have merely fractured it.
Oh, I see.
Instead of a single trackable bullet, you have now created a shotgun blast of highly radioactive debris. And much of that debris is still on the exact same trajectory toward Earth.
So you basically turn a localized kinetic strike into a global radioactive meteor shower.
Exactly. You multiply the problem.
Okay, so nukes are out, which leaves the kinetic impactor. But what does that actually mean? You just crash a spaceship into it?
Essentially, yes. You rely on the conservation of momentum. You take a spacecraft, which has a specific mass, and you accelerate it to a phenomenal velocity, around 14,000 miles per hour. You navigate it autonomously, and you crash it directly into the asteroid.
I know you want to explain the math, but I am going to use an analogy, and I am strictly reserving this for DART. It is exactly like a game of cosmic billiards.
Billiards, okay.
The asteroid is the 8-ball, and humanity just built the cue ball. We slammed our cue ball into the 8-ball to change its direction.
The billiards analogy is perfectly accurate for the transfer of kinetic energy. When the spacecraft impacts, it imparts its momentum into the asteroid.
But the spacecraft is tiny.
Yes. The spacecraft is incredibly tiny compared to the mass of the asteroid. The impact doesn't knock the asteroid wildly off course immediately. It imparts a microscopic change in velocity, a metric we call delta V.
Delta V, change in velocity.
Right. We are talking about changing the asteroid's speed by millimeters per second.
Millimeters per second. That sounds entirely useless if a mountain is hurtling toward us at 40,000 miles an hour.
It is useless if you do it a week before impact. But the physics of orbital mechanics rely on time.
Time is the lever.
Exactly. If you apply that tiny delta V 10 or 20 years before the predicted impact, that millimeter per second alters the angle of the orbit infinitesimally. But over the vast distances of millions of miles of space travel, that microscopic angle change compounds.
So a millimeter shift today becomes a 1,000-mile miss a decade from now.
Precisely. It is all about early detection.
Right. So the NEO surveyor finds the rock early so DART can hit it early, giving the tiny nudge enough time to push it off the tracks. And the DART mission actually proved this works, right? They didn't just model it on a supercomputer.
They executed it perfectly.
Tell us about the target.
They targeted the Didymos binary asteroid system. Specifically, they targeted Dimorphos, a small moonlet orbiting the larger asteroid Didymos.
Why a binary system? Why not just a single rock?
It was a very smart choice. They chose a binary system because by altering the moonlet's orbit around its parent body, scientists could measure the change in orbital period precisely from Earth in a matter of weeks.
Oh, because it passes in front of the bigger one.
Yes. Rather than waiting years to measure a change in a solitary asteroid's orbit around the sun, they could see the effects almost immediately. The impact successfully shortened Dimorphos's orbit, proving beyond a doubt that a kinetic impactor can alter the celestial mechanics of an asteroid.
That is awe-inspiring. We fundamentally altered the mechanics of the solar system.
We did.
We moved a celestial body. It proves that humanity is no longer guaranteed to be a victim of the cosmos. We aren't the megafauna from 12,800 years ago, just staring up at the sky in total ignorance.
No, we are not.
We possess the physics, the engineering, and honestly, the sheer audacity to reach out and move the heavens to protect our planet. Which brings us to the ultimate thesis of this deep dive.
A bigger picture.
Right. When you synthesize all of this, the sheer scale of the threat, the complexity of gravitational keyholes, the necessity of space-based infrared telescopes, and the physics of kinetic impactors, it forces a very stark realization about who we are as a species.
It really does. The overwhelming takeaway is that planetary defense cannot be a nationalized effort.
It is too big.
It is, by its sheer mechanical necessity, a globally unifying force. Think about the nature of an object like Apophis or a hidden city killer emerging from the sun's glare.
Yeah.
An asteroid does not recognize sovereign borders. It does not care about terrestrial geopolitics, economic sanctions, or ideological divides. It is an indiscriminate existential threat to the entire biosphere.
And the resources required to defend against it are just too massive for any single entity. I mean, no one country has the monopoly on the entire night sky.
Impossible.
We need radar arrays in Australia, telescopes in Chile, data processing in Europe, and launch capabilities in the US and Asia just to maintain the observational network.
Exactly. The pragmatism of survival demands global unity. Deflecting an asteroid requires overlapping fields of observational view, open source data sharing at the Minor Planet Center, and the combined technological and financial resources of the entire developed world.
Because if one link breaks, we all fail.
If one nation attempts a deflection and fails, or miscalculates the delta V and accidentally pushes an asteroid into a keyhole, it dooms everyone. The margins of error are too small and the consequences are too absolute for anything less than complete planetary cooperation.
It is the ultimate test. It is almost a poetic forcing function for our civilization. If you think back to our opening scenario, the breakdown of supply chains, the evaporation of the economy, the collapse into survivalism.
Well, the dark timeline.
Yes, the only way to prevent that dark timeline is by prioritizing our shared survival over our localized divisions. We have to share the data. We have to collaborate on the kinetic impactors because the universe simply doesn't care about our squabbles.
It does.
If we let our terrestrial conflicts distract us from the sky, the mechanics of the solar system will make those conflicts irrelevant very, very quickly.
It is a profound shift in perspective, looking at near-Earth objects not merely as a terrifying hazard, but as an external evolutionary pressure.
An evolutionary pressure, I like that.
It forces humanity to mature, to operate on a species level rather than a tribal one. Planetary defense might be the ultimate catalyst we need to recognize that we are unequivocally a single crew on a very fragile ship.
What a phenomenal place to land. Let's briefly recap the ground we have covered today.
We covered a lot.
We did. We started in that cold observatory at 3 a.m., mapping out the terrifying cascade of discovery, disclosure, and the immediate societal collapse that precedes the incredible kinetic violence of an impact.
The thought experiment.
Right. And then we explored the deep geological evidence of the Younger Dryas impact 12,800 years ago, and how a rapid climate shift can completely reset civilization.
The impact winter.
Then we confronted the modern reality of Apophis, unpacking the nerve-wracking math of its 2029 near-miss and the terrifying reality of gravitational keyholes and the Yarkovsky effect.
The tiny thrusters.
Yes. We stared into the blind spot of our own sun's glare, acknowledging the city killers hiding in the light. But we did not leave you defenseless. We explored the cutting-edge infrared technology of the NEO Surveyor and the historic, undeniable success of the DART mission, proving that a kinetic impactor can alter the destiny of a planet. We moved from the fear of a cosmic reset to the awe of human capability.
And as we close this analysis, I want to leave you with one final thought to consider on your own.
Please do.
We know from the geological record that the universe is capable of resetting the board without warning. Today, for the first time in the 4.5 billion-year history of the Earth, a species exists that has the mathematical comprehension, the infrared optics, and the kinetic tools to stop the next impact.
We actually have the tools.
The capability is no longer theoretical. But the ultimate test isn't a matter of engineering. The ultimate test is whether our shared instinct for survival is strong enough to make us coordinate those tools together before the sun's glare reveals something we are not ready for.
A brilliant, sobering, and awe-inspiring thought to leave on. The universe is a complex, dangerous mechanism, but we are finally learning how to read the blueprint and, more importantly, how to change it. Thank you for joining us on this incredibly deep dive in the Mind Lounge. Keep your imagination sharp, keep your critical thinking engaged, and whatever you do, keep looking up. We will catch you on the next one.